Hello everyone, welcome back to Nated Engineering. Today we are doing an exercise on air compressors, power machines and 6. It's an exercise that I've taken from a question paper that was written on April 2019. It's question number 5 and it reads as follows. A two-stage single-acting reciprocating compressor takes in 54,000 centimeter cubed of air per cycle at a pressure of 100 kilopascal and a temperature of 26 degrees Celsius, whilst rotating at 300 revs per minute. The air is compressed to 400 kilopascal in the low-pressure cylinder, while volumetric efficiency of the low-pressure cylinder is 89%. The stroke length of the low-pressure cylinder is 1.2 times the diameter of the piston. The index for compression for both cylinders is 1.2, and the intercooler extracts 26 kilojoules of heat per second. Take R for air as 0.288 kilojoules per kg Kelvin. Specific heat capacity at constant pressure for air is 1.008 kilojoules per kg Kelvin. And calculate the following quantities. Those are the question. Question number 1. Mass of air delivered by the compressor in kg per minute. Question number 2. Absolute temperature of the air after compression in the low pressure cylinder. Question number 3. Absolute temperature of the air at the inlet to the high pressure cylinder. And question number 5.4. For the low pressure cylinder, 5.4.1, swept volume in cubic meters per stroke. 5.4.2, diameter of the piston in millimeters and the stroke length in millimeters. And then we go to question number 5. Volume of air taken in by the high pressure cylinder in cubic meters per stroke. And this is the information that we are given. We are given the effective volume, we are given the rotational frequency, we are given the volumetric efficiency, and then we are told that the stroke length is equal to 1.2 of its diameter. This is in the low pressure cylinder. And then we are given the index of polytropic, we are given the heat lost to the intercooler, and then we are given our gas constant and our specific heat capacity. And then question number 1, which is 5.1, they say mass of air delivered by the compressor in kilojoules per minute. It's 5.1. They are looking for the mass in kilojoules per minute. We are going to use MRT. It's equals to PV. This is what we are looking for. Gas constant we do have. Our T1 we do have. We're going to use the information of number 1. We're looking for what? The mass that is delivered. We know the mass that is delivered is associated with the effective volume. Since we do have the effective volume, that's what we are going to put here. And then we make mass the subject of the formula, which will give us P1 V effective divided by the gas constant times a T1. What is our pressure number 1? Pressure number 1, it's 100 kilopascal. Effective volume, this is our effective volume. It's 0.054. Gas constant, 88. T1 is 299. This will give us kgs. But we are looking for kg per minute. That is why we are going to divide by the rotational frequency here, which will be 300. We know it's revs per minute, which will give us kg per minute. And that is the SI unit that they said we must have. And then our answer, it's equals to 18.813. And then we go to question number 2. They say absolute temperature of the air after compression in the low pressure cylinder. We are looking for the temperature of the air after compression, which will be before the intercooler in this point. We're going to use T2 minus divided by T1. It's equals to P2 divided by P1 raised to the index minus 1 divided by the index. What are we looking for? We are looking for T2, temperature number 2. We make it the subject of the formula, which will be T1 P2 divided by P1 N minus 1 divided by N, and then you substitute. This is T1. T1 we do have. It's 299. Pressure number 2 is 400. This is 1. Pressure number 1, it's 100. The index, it's 1.3. Minus 1 divided by 1.3, which will give us our T2 as 411.726 Kelvin. That is the temperature of the air before the intercooler. And then we go to question number 3. They say the absolute temperature of the air at the inlet to the high pressure cylinder. Now they are looking for the temperature of the air after the intercooler. What is it that we know associated with the intercooler? We know that the energy that was lost to the intercooler is 26 kilojoules per second. So this is the formula that we are going to use. This is 5.3. The formula that we are going to use is Q. It's equals to mass times the specific heat capacity times the change in temperature. This is our Q, mass of air times the specific heat capacity. Change in temperature will be the temperature. At this point, let's say this is 2 prime. Will be at the temperature at point number 2 minus the temperature after the intercooler, which will be 2 prime. The temperature that we are looking for is this one. We have everything here, so we just need to substitute. But remember, this it's in kilojoules per second, and we have our mass in kg per minute. So first we must fix that problem. Here we are going to say 26 kilojoules times 60 to make it kilojoules per minute. And then we say the mass, we put it as it is. Our mass is 18.813. Specific heat capacity we are given as 1.008. 1.008. And then open bracket. Our T2 we just calculated. It's 411.726 minus this is what we are looking for. Then from here we solve for this. Since this is the only unknown in our equation, we get that our answer is equals to 329.463 Kelvin. And then we go to question number 4. They say for the low pressure cylinder. Everything that we are asked to calculate below, it will be for the low pressure cylinder. 5.4.1 swept volume in cubic meters per stroke. It's 5.4. We're doing 5.4.1. They said we must calculate for the swept volume in cubic meters per stroke. We are given the volumetric efficiency, and they said it's for the low pressure cylinder. In this question, they said what we're calculating is for the low pressure cylinder. Therefore, we're going to use this low pressure, the volumetric efficiency rather. We know it is equals to the effective volume divided by the swept times 100. This we are given. The volumetric efficiency is equals to 89. It's equals to, what is the effective volume? The effective volume is 0.045. This one we're given. We're looking for the swept times 100. The swept volume is equals to 0.0607 cubic meters. And then we go to 5.4.2. They say diameter of the piston in millimeters and the stroke length in millimeters. What is it that we know about the swept volume and the stroke length? We were told that this is the condition that they gave us. The stroke length, it's 5.4.2. We're told that the stroke length is equals to 1.2 of its diameter. This is the low pressure cylinder. We are dealing with the low pressure cylinder here. Where do we get one of these? In which equation do we get one of these? When we are calculating for the swept volume. We know swept volume is given by pi divided by 4 times the diameter squared times the stroke length. We do have the swept volume. The swept volume we just calculated. This is our swept volume. Let's substitute 0.0607. It's equals to pi divided by 4. Do we have D? No, we do not have any diameter. But we know that the stroke length is equals to 1.2 of its diameter. Therefore, this will be pi divided by 4 times 1.2 times D cubed, 0.067. This is the only unknown in our equation. We solve for the unknown, and I got that our diameter in millimeters, since they said we must calculate in millimeters, is equals to 400.8 millimeters, which is equals to 401 millimeters. Yeah, just put it at 401. And then from here, we are going to say our stroke length, since they said we must calculate for this and the stroke length as well. Our stroke length is equals to 1.2 times the diameter, which our diameter we already know it's 401, and this will give us no, let's put it as it is. This will give us our stroke length as 481 millimeters. And then we go to our last question. We will use the formula. This is 5.5. We will use MRT. It's equals to PV. We're going to use the information of the second cylinder, since they are talking about the high pressure cylinder. Here it will be P2 and here it will be T2. This is the effective. We're looking for the volume of air taken in, that is the effective volume. We're going to use the effective mass so that we are able to use, so that we get the effective volume. Gas constant we have. We make this the subject of the formula. This will be mRT divided by P. Here we are going to get cubic meters per minute. Why? Remember our mass, we got our mass in kg per minute. They said we must get it in cubic meters per stroke. Therefore, we have to divide by the rotational frequency. Since we know the rotational frequency, it's rads per minute. These two will cancel out. Therefore, we are going to say times here the rotational frequency, and then we substitute. Our mass, it's equals to 18.813 times the gas constant is 0.288 times our T2, it's 329.463. Our pressure, which will be pressure number 2, it's equals to 400. And then our rotational frequency, it's 300. And then from here, we are going to get our volume as 0.0149 cubic meters. And then that's how we go about answering this question. I will see you on the next lesson.